Okay. Hello. I'm Bo Hyung Han, National University. We are going to start the winner presentation session. As mentioned earlier, our workshop hosted two challenges. One is for recognition, and the other is for retrieval. The first winner presentation session is about recognition. We have three presenters ready. Actually, the winner of the two challenges are same. The winner for the both challenge, Team Dieter, is going to present their method first. Please welcome the winner, Team Dieter.
Hello. So nice to be here. Let me share my screen. Okay, can you see the presentation?
Yes.
Okay, great. So I'm happy to present both solutions actually. Although we are just speaking about the recognition challenge, both solutions are pretty similar in terms of modeling and are just different in post-processing. So I put both presentation into one basically. So about myself, I work at NVIDIA. I have a PhD in mathematics from the LMU in Munich. I joined Kaggle 4 years ago, did more than 50 competitions since then, have multiple first places, and I'm currently ranked #1 in the world on Kaggle. Also due to this competition, where I was really lucky to win both parts. So maybe I could say for, let's say, the high class Kagglers, the points attributed for this competition are more worth than any prize money. Maybe that's feedback from my side to the organizers. So quickly, let me recap. The challenges of this competition was the long-tailed class distribution with high class intra-variability. So you can have landmarks with very different views inside, outside of museums and kind of those things. There was, as Tobias mentioned, a restricted inference environment, which was like 1 GPU and 2 core CPU with restricted runtime of 12 hours. There was a tight timeline for competitors of 7 weeks. And there was an open source of last year's solution, which used the same data set. So it was quite difficult to distinguish from other top participants, especially from those who were quite successful in the last year. So my strategy from the beginning was to focus on local features because I thought there's a lot of room for improvement from my side, but not to use any special verification like Runzack, because I think it has a bad cost-benefit ratio, especially with this restricted inference environment. So I focused on using rather new methodologies and new models, which have a built-in leveraging of local features. And I also used the retrieval approach for the recognition challenge. So you can do a classic classification using a softmax layer, but you can also use for the recognition challenge and a retrieval approach. And I think that was done by most teams also because it proved quite valuable in the last year. As a resources, I used PyTorch with mixed precision and distributed data parallel on a DGX1, and I used GitHub and GitHub Actions to basically synchronize my local code with the Kaggle environment, so I don't need to set up anything there. What is quite important is how we validate. I used the 2019 test data for recognition, which was provided including labels after the competition 2019. Because there you actually have non-landmarks and that are quite important for evaluating your models. And for the retrieval, I used also the 2019 query index dataset. And for evaluating my models, I tracked the competition matrix. So global average precision and micro average precision at each of the end of each epoch. So my solution is basically 2 new model approaches or very recently developed model approaches. One is based on DOLC, DOIC stands for Deep Orthogonal Local and Global Features, and was published in August, I think, on Archive. And the idea of this DOIC model is basically to have two separate parallel branches. One is handling global features and one is handling local features. And then you have an orthogonal fusion module, here shown in yellow, which basically combines both features and is responsible for the model to learn the two things really separately. What I did improve compared to the paper is that I added a few layers of EfficientNet for encoding of my model and was able to use larger images by this. What I also used differently than the original paper was to use a subcenter arc phase loss, where you basically, for each landmark class, you have a small center, in my case, a center of 3. So you can learn slightly different embeddings, so you can deal with the high intra-class variability. And this was shown by a top performing team last year that this outperforms classic arc phase. And at the end, I predicted the 81,000 classes. What is quite important is my training recipe, and I also used something that was popular last year and was shared by top teams, namely to start training on the provided GLDV2 clean data set, to train a few epochs on small image size, but then extend image size and the data set. I called it GLDV2X, and that's basically part of the original GLDV2, but a subset restricted to those 81,000 classes. So GLDV2 originally has 200,000 classes. So I used the 81,000 classes of the clean data set, but added the noisy landmarks of the same labels. So the model also needs to learns to deal with more noisy images and also see more different angles and aspects of images. And at the very last step, I fine-tuned a few epochs on even larger images. For augmentation, I used cutout as the main augmentation for regularization, and then also shift, scale, and rotate. And I use standard ADAM optimizer with cosine, schedule, and weight decay. The second model also is focusing on local features, I would say. There I combined a swim transformer, which is recently used for computer vision, and that's something that is distinguishing to last year, where I think vision transformer was not so popular. And also there I added an EfficientNet encoder instead of the original patch-based embedding, which not only lets me deal with larger images, but also creates a more sophisticated embedding of the image patches. So I have an EfficientNet encoder, then I feed through a swim transformer. I use the representation of the virtual node, feed this to a NAC, which is basically just a fully connected layer plus batch norm plus Prelo activation, and then use the same subcenter arc phase losses in the previous model. Also here, the training recipe is quite important, and it's very similar to the one before, with 2 minor edits, which mainly deal with how the swim transformer is set up, namely having a fixed input size. So in this example here, I used a swim base with a 2 to 4 image size, and that's basically fixed and you cannot change that. So what I did is I started training only the swim transformer on the 2 to 4 image size on the GLDV2 clean, and then added the EfficientNet backbone and wanted to train on medium images, meaning double the image size, so 448. But to make this work, you want to not get any NAs in training, you basically need to freeze the model you have trained in the first step, add the EfficientNet and just train the EfficientNet for one epoch to basically let the newly added EfficientNet adjust to the rest of your model. After this one has been adjusted, you can unfreeze the whole model and perform this, the third and fourth step, same as the model before. So a lot of epochs on medium image sizes, and then a few epochs fine-tuning on very large image sizes. And I use the same augmentation and optimizer and learning rates as in the model before. So those were really strong architectures that I think especially deal with local features very well and help to combine local and global features in one model. For post-processing, and here I also depart from my retrieval solution. So for recognition, I basically use an additional data set from 2019. So the test data set of 2019, which I said that contains non-landmarks. And I basically re-rank my model predictions by subtracting also the cosine similarity to non-landmarks. So by this, you basically can identify non-landmarks very well. That's the first step. So you have your model predictions, you perform cosine similarity between your test set and the train set within the kernel. You subtract the cosine similarity between any test set and the non-landmark set, which already gives a really, really good improvement. But additionally, you can also downrank basically your train images, because also the train images have still a lot of noise, and with this cosine similarity between train and the non-landmarks, you can also identify a few non-landmarks in your noisy train set. And for retrieval, I want to also mention here quickly, I use the discriminative re-ranking, basically leveraging the recognition side of the model. So for the query dataset and for the index dataset, the idea is to label both datasets in terms of landmark class, and then you uprank if the predicted label matches, and you downrank if the predicted label does not match. And compared to another solution that was done 2019, I used the soft upranking and downranking by just adding the confidence or cosine similarity of the labeling basically to the cosine similarity between query and index. And by this, I also had very good performance in the retrieval side of this competition. So in total, you can see on the left, that was my total model ensemble that I was able to fit into the 12 hours of runtime. I have 3 different DOLC models with different EfficientNet backbones. I have 3 different hybrid spin transformers with EfficientNet backbones. And I also have some classic EfficientNets for diversity. From a training perspective, each model takes around 7 to 10 days on the DGX1. And you can see my results on the right side. So I was lucky to win both competitions with quite some margins to the teams after me. So with that, I would jump into a few questions if there are any.
Oh, sorry. So we are behind the schedule. So we are going to take the question at the end of the session, after all the 3 talks.
Sure.
Okay. Thanks. All right. Let's move on to the second presenter. Second presenter is ByteDance Vision Tech. They are at the 3rd place of the recognition challenge. Please start.
Christoph, I think you need to stop sharing your screen, maybe. Okay, can you hear me?
Yes.
Okay, let's begin. Hello, everyone. Our team is ByteDance Vision Technology, which comes from ByteDance Incorporated. We're honored to share our solution of Google Landmark Recognition Competition 2021. This slide shows the whole solution, which aggregates retrieval score and classification logics. The whole solution can be summarized as the following recognition pipeline. Firstly, we use distractor score and classification logic to adjust the raw retrieval score. Specifically, we calculate raw retrieval score, which is a quotient similarity between the input image feature and the private train site to obtain top 7 candidate images. Then the distractor score is computed to add penalization for non-landmark images, which is similar to last year's top 1 solution. More important, we find that it is crucial to use classification logics to support predictions. The classification logic could be viewed as the quotient similarity between the image feature and the learned class center by archviz. It is complementary to retrieval score, especially when there are few images of some landmarks in the private tree. So we look up classification logics of top 7 retrieved image and add them to corresponding raw retrieval score to obtain final retrieval score. Meanwhile, we found that the accuracy of pure top 1 classification is very high. So we add another pair of top 1 classification landmark ID and logic into previous top 7 candidates. Note that this top 1 classification logic doesn't have a distractor score because it is not from any retrieved image. But this turns out not to be a problem because we found that top 1 classification logic has some robustness to some non-landmark images. Finally, we could get top 7 candidates with their final retrieval scores plus 1 candidate from top 1 classification. Then we calculate these candidates' scores with their labels to get final prediction. And this slide shows our model training procedure and some experiment results. As with previous top 3 solutions, our model architecture is shown as this left figure, where backbone outputs are aggregated via a gem pooling and then fed into an embedding neck layer. The image embeddings are used to classify specific landmarks supervised by archviz laws with adaptive marking. And here, the gem pooling is removed in transformer and hybrid-based models because we think each token output feature is already the global representation because of the self-attention mechanism. Considering the diverse of model architecture, we choose 3 types of backbone, which as follows: the same-based models, including efficient light B5, B6, B7, and Version 2. The transformer-based model, we choose swing large, and hybrid-based model, we use the CVT W24. We found that compared with those same models, swing large and CVT lead a more significant improvement of the final ensemble performance. Similar to last year's solutions, we adopt a multi-stage training with different image resolutions and train splits to accelerate network convergence. Our train schedule could be divided into 3 stages. In stage 1, Go landmark V2C is used to classify 80,000 landmarks. In stage 2, Google landmark V2X is used, and the weights from stage 1 are used to pre-train. In stage 3, 4 Google landmark Version 2 is used to classify 200,000 landmarks for the classification logics. The weight from stage 2 is utilized to pre-train. It is experimented that the 4 Google landmark Version 2 couldn't further improve the discrimination of my embeddings, so we only optimize the classification height in this stage. Okay, more train details, please see our solution paper. Some results are shown in right table. For swing large, adding the classification logic to raw retrieval score can bring 0.03 improvement in private score. And adding top 1 classification logic could bring 0.027 in private score for B5. During the ensemble process, we concat 7 model features to contact the ensemble retrieval to get raw retrieval score and distractor score. And we design some models to generate classification logic and top 1 classification logic. Then the whole recognition pipeline is employed to obtain 0.489 private score. Okay, thanks for your listening. If you are interested to our solution, feel free to contact us.
Thank you so much. Okay, let's move on to the third presenter. The not enough fitting. This team takes the 5th place in the recognition challenge.
Hey everyone. So yeah, do you mind start sharing? Okay, cool. Let me share my screen. So I only have 1 slide, so I will keep it short. So this is our fifth place solution, and we also ranked the 7th in the Google Landmark retrieval. This is Long Chening, and I'm a software engineer at Instagram. So I'm doing this competition while I'm on leave. I'm on parent leave from my regular work, and this is a really intensive competition for me, and also especially for the last 2 weeks. And so as an individual participant, so I have very limited computation resources. So compared to like other models, I'm trying to focus myself to design a new architectures so that it can be efficiently trained, also like perform good like in terms of like accuracy or like MAP. So the basic idea is like we want to merge the feature maps at different scales. So for and use the aggregation techniques we are using is based on the VRAD. So specifically, it's the next VRAD. So the core ideas of the VRAD is use residual to multiple centroid on the measurements at the high dimensional spaces, so they can aggregate those feature maps into one high dimensional vectors, and we just simply concatenate and do a linear projection to a lower dimensional vector to reduce the redundancy. So for example, we fetch the 3 feature maps from the backbones. For example, this one is that we have the 28 by 28 with 512 channels, and another like smaller one but higher number of channels. So I first tried to use the net VRAD. So that one is like it's not really perform really good. And then I tried to use the next VRAD. So that model is basically used for the YouTube AM like video classification challenge. And the good part is that the basic idea is like it can decompose a high dimensional vectors into several lower dimensional vectors. So with different groups. So for example, in the first one is like with 2000 channels, we use the 8 groups and 128 centroid. And for the 1000 channels, we use 4 groups and 128 clusters, the same. So that will result in around like 30,000 dimensional vectors. And then we just concatenate these 30,000 vectors into like 90,000 vectors, very long, high dimensional. And then we just project to a vector of 512. So for the training strategies, we fix the backbones only and train the learnable pooling on V2 extension, which contains around like 30.2 million images with 80,000 landmarks. So with the image size of 256, and then the second step, we fine-tune the whole model only on the 1.6 million images, and so that make it more efficient. And the last steps, we do the transfer learning, and we fix the backbone again, and only train the learnable pooling layers on V2.4, which is like 4.1 million. And also we also include the land landmarks in these steps. The one thing to mention is that on the first 2 steps, we use the subcenters, and the last one is that we only use the arc face. So yeah, we also apply like dynamic margins and to tackle the problem of imbalance, class imbalance, and also we use the pre-computed embeddings on V2.4 for inference, similar to last year's winning solution. Yeah, I think that's mostly the most important part of my solution, and I will keep it short and leave more time for the Q&A.
Okay, thank you so much for all presenters. As Andre mentioned in the chat window, there are technical reports for the method of the first place and the third place. So if you have any, if you're interested in their method, you can refer to the technical report. And there are a couple of questions in the chat window. The first one is for the Christoph. The question says, your method seems to be a combination of a large number of components. Do you have any idea which component would cost you the most in performance?
I would say dealing. I can say what costs the less performance. So not using the very large images, but medium-sized images would have probably the best cost-benefit ratio, I would say.
Right. Another question for you. 30 or 40 epochs for medium-sized image. What does one epoch means?
Yeah, exactly what exactly that. Iterate over every image. So in this training step, there are basically 3 million images. So for 30 to 40 times, you iterate over those 3 million images.
Right. Thanks. A quick question for the ByteDance team. There are 5 team members in your team, but there are 9 people listed on the paper and the slide. Is everyone the part of the team?
Okay. Actually, our team has 9 people, and only five persons are joined to submit predictions for the Kaggle computation, and the contribution of other 4 persons is to help train the model and give some useful discussion.
All right. All right. Raj, okay, so since we are substantially behind the schedule, then we have to stop here. Okay, let's move on to the next session. Thank you so much for joining the winner presentation session. Thank you.
So just one comment before we move on. So I think the speakers in the winner teams are still available. People can still ask questions via the chat since we don't have time to answer answer questions during live. Feel free to ask questions in the chat and hopefully the speakers can reply there. So now moving on in our schedule, I think Thorsten will host our keynote talk. Thank you.
Yeah, it's my pleasure to introduce our first keynote speaker, Laura Leal-Tergé.